Welcome to another lecture in Cyber AI. Today is an important milestone here in the course. For the past few weeks, we've been focused mainly on cybersecurity foundations, and that background was essential because really you can't build intelligent defenses without first understanding the landscape that you're trying to protect. Starting today, we're going to be building or learning about building that artificial intelligence or AI side of Cyber AI. Specifically, we're going to explore machine learning, often abbreviated ML. This is the practical core of AI as it's used in cybersecurity. When I say machine learning, you might already have some ideas, maybe voice recognition on your phone, some recommendations for what YouTube video to watch next, or even ChatGPT. All of those are definitely powered by machine learning, but our focus will be narrower and more applied. Because it's a Cyber AI course, we're going to be focused on how machine learning allows us to detect attacks, classify malware, spot anomalies, things like that. We're going to begin with the basics, though. What is machine learning and how is it different from traditional programming? And why does it matter for security analysts? This is where we lay the foundation for what we're going to be building from here. So first off, let's look at the agenda, our roadmap for the first part of the lecture. We're going to try to pin down a definition of ML, of machine learning, both historically and in plain modern terms, and we'll compare it to traditional programming because that contrast is the easiest way to see what makes ML so different. Then we'll introduce some basic vocabulary. We'll talk about inputs, outputs, model, training data, testing data, and so on. And we'll bring it back home to cybersecurity and talk about why machine learning is not really just a cool technology, but it's definitely necessary in modern defense. So some of that history, a couple of fundamental quotes here. Arthur Samuel from 1959 talking about machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. Think about the programs that you've made in the past. You've told the program, you've told the machine exactly what to do and in exactly what order. Sometimes things might go wrong, of course, but you've generally told it what to do and in the correct order, and hopefully anyway, and you've then been able to make a program, but you had to explicitly program that. And again, by explicitly, I don't mean using a lot of swear words in the comments. I'm talking specifically about the order that you're placing things in the program. We're talking about something that's learning on its own. It's not being explicitly programmed. The line by line isn't being explicitly placed in there. Also, Tom Mitchell from 1997, a program is said to learn from experience if performance improves with the experience. So we're assuming that the program is learning as it's going and it's improving as it's going. These are still great summaries, really, as we think about programming and as we think about machine learning and the word learning there. Really expanding on what Tom Mitchell said, a computer program is said to learn from experience. Well, that gets a little bit more complex. Experience, E, is the data. So the experience is that data that a program has or that the machine learning has access to. And that data is related to a task. And then we measure that data based on a performance measure, or P. Think about tasks as being defined as T. So we're able to then measure, is this program, is this machine learning algorithm actually improving? Because we're measuring that performance. We're setting it up as being measurable. So you can really think of machine learning in either definition, the more formal one or the simpler definition from Arthur Samuel. The key idea is this: machine learning means improving performance by using data, not by rewriting code. Let's dig even a little deeper into that, because we can contrast machine learning with traditional programming. In traditional programming, you as the developer write down those rules explicitly. Imagine we're building a program to detect spam. We'll go back to that spam email detection example often because it's easy for everyone to grasp, right? We can think about spam emails, but we need a way to detect them. If we didn't have methods for detecting spam, we would be inundated with spam, even more than we might be today. So we might build a program with some rules in it. If the subject line contains the phrase free money, maybe we mark it as spam. If the message has more than 3 exclamation points, maybe we're suspicious of it. If the sender isn't in your address book and there's an attachment, maybe flag it. And if we think about the rules that must be behind that, they're hard-coded rules. So that free money rule is a hard-coded rule. The program that we make to detect spam doesn't know what spam is. It's just following the rules that we wrote. And it's fine for a while, but what if somebody actually wrote you and wanted to give you some free money? Or what if the spammer decided instead of FREE to define free money, they did FR33? Well, now our program breaks, or they spell money with a 0 instead of an O. Now that program breaks, and we have to go back in and try to figure out every way that the spammer might send a variation of the words free money in the subject line and mark that accordingly. But we have to manually go in and reprogram that every time the spammer does something different. Contrast that with machine learning, where the approach is just flipped. Instead of us writing the rules, we give the system a lot of examples. We give it thousands of spam emails and thousands of legitimate emails. We've labeled them accordingly. We've labeled them, pre-labeled them. We know that these are spam messages. We've labeled them as spam, and we feed that in. We know these are legitimate messages, and we feed those in, marked as or labeled as legitimate. System then uses an algorithm to infer the patterns. What distinguishes spam from not spam? Maybe it notices spam messages often contain certain types of URLs, or legitimate emails are more likely to include signatures at the bottom of the email. Whatever it is, that algorithm determines what makes a spam mail look like a spam mail, and what makes a not spam mail, a legitimate email, what makes that look legitimate. The rules don't have to explicitly be written by us, though. They're discovered by the system through exposure to data, through that experience. And as new data arrives, as more experience, as the system gets more experience, maybe more spam or maybe more legitimate emails, or more than likely both, the model can adapt without us rewriting code. So as spammers change their tactics, the model can be updates itself, such that it now knows that these are spam emails. Core concepts for machine learning are important, and one of the challenges in learning machine learning, or learning about machine learning, is sometimes just simply the vocabulary around machine learning, because it is different than what we might consider it coming from a traditional programming or a traditional computing background. What's called a feature in machine learning is something that we would consider an input. So something about the data itself. The inputs are what are known as features in machine learning, and the outputs are the labels or the predictions, what the system tries to produce when it is working. So think about all those terms being interchangeable as we work through machine learning and as we learn about that vocabulary. The model is the mapping that is between the inputs and the outputs. Training versus test data. We're going to have test data that we are going to be testing the performance of the model with, versus training data. Training data is something that maybe we've labeled already. We know that these are spam versus legitimate emails, and so we train the model. Hey, look, all of these messages we just fed in are spam. So take a look for patterns in those spam messages. Or we feed in legitimate emails and train it to say these are legit, and this is what a legit email looks like. These thousands of messages are all legitimate. And then we can take, say, a few thousand messages that aren't labeled, that aren't marked as spam versus legitimate, and feed those in, find out how well it does. Now, maybe behind the scenes, we've already pre-labeled those, but we've just removed the label. So we know we're able to quickly then deduce how well the algorithm did, how well that model did, but we can then find out the performance of that model. And then generalization is where we end up trying to apply what's been learned to data that's not been seen before. So we're training and testing those models, finding out how they perform, trying to help them perform better. And then finally, we're getting to that generalization around it. Let's look at that spam filter example again and really dive deep into it. In the old days, spam filters were rule-based. They looked for words like prize or free. They checked if the message had lots of exclamation points, etc. So those were hard-coded rules. But an ML-based spam filter works differently. It trains on all sorts of labeled emails. So again, this is spam, this is not spam emails. And it might, again, learn that those emails contain certain phrases. Maybe they have links in them that are suspicious. Maybe they're not a .com link or a .edu link or something that's one of the common top-level domains. And not that that's, again, necessarily going to be indicative of spam, but it might be one of the factors that spam emails have in them. More commonly, we might look at that. So then the model can pick up on the patterns that humans might not notice. Maybe there's a statistical frequency of a certain word or certain word combinations. Maybe it's the structure of the header, maybe case sensitivity, those types of things. As more data arrives, then the filter adapts and it learns the tricks that the spammers have, and it's updating its rules automatically. That adaptability is exactly why machine learning has taken over for spam filtering in practice. Gmail spam filter, for example, is powered by machine learning and not static rules. Let's look then at why machine learning matters in cybersecurity. You might have already guessed. Well, spam is something that is related to cybersecurity, not allowing spam or phishing-style emails in. But if we look at it as well from a data volume standpoint, there's just too much data to look at manually. The sheer volume is overwhelming. Modern networks generate millions of packets per second. Logs grow at a rate that no human analyst could ever keep up with. So without automated methods, defenders are just drowning in data. The second, threats evolve constantly. A rule-based intrusion detection system it's like a locked door, which works, right? But it has a simple key. Attackers just can make a copy of that key or try a different entry point, and the system is bypassed. So if we had a door with a key on it, maybe an alarm on that door to detect the intrusion, or some type of bell, something that alerted us when that happened. Well, if an attacker knew that, they could just go to the window and open up the window. Third, machine learning allows us to detect subtle evolving patterns that really would be hard to notice. A spike in unusual DNS queries might be one. Change in user login times. They normally log in at this time, but now suddenly they're logging in at 2 in the morning from a different IP address than normal. Or maybe there's a different way to do a phishing URL, something like that machine learning model will really excel at detecting, especially across large data sets. That's why machine learning underpins so many modern security tools, intrusion detection systems, malware classifiers, and so on. It's great at spotting anomalies. And without it, defenders wouldn't be able to keep up with that complexity and the scale of the landscape today. Some of the key takeaways from this first part: machine learning learns patterns from data. It doesn't have just fixed rules. And think about the core concepts, the inputs, the outputs, the models, generalization. Refer back to that slide again for how those things are referred to when we think about machine learning features and labels and so on. And when we work with cybersecurity, we're applying AI to cyber, creating that CyberAI. We need machine learning for scale. We need it for adaptability. We need it for speed because we need to keep up. We can't possibly keep up with everything that's happening now. Now that we've laid out the general idea of machine learning, it's time to look at one of the two main branches, supervised learning. This is probably the most widely used form of machine learning, both in industry and cybersecurity. If you've ever used a spam filter, a recommendation system, or even a voice recognition program, you've interacted with supervised learning. And today we're going to go into what supervised learning means and how it works. Also, some of the different kinds of supervised tasks and where it shows up in cybersecurity. We're also going to talk about the strengths and weaknesses and why, despite being powerful, supervised learning isn't always enough by itself. So we're going to start with a definition of supervised learning. We'll define that term as part of what we're doing. And then we're going to look at classification versus regression, training workflow, some cybersecurity applications, and then limitations and challenges around cybersecurity and supervised learning. So what is supervised learning? Supervised learning is all about labeled data. Each example in the dataset comes with both inputs and outputs. Inputs, again, are the features. They're the measurable properties of the data. The outputs are the labels, the truth that we want the model to learn, spam versus not spam. You can think of it like teaching a child with flashcards. You show them a picture of a dog and say, this is a dog. You show them a picture of a cat and say, this is a cat. Over time, the child learns to associate visual features with the labels. We've labeled dog and cat. We know what those are, and we know what those look like. And so that's supervised learning. It's just training on labeled examples, and then being able to predict labels or predict the outcomes for new and unseen data. When we think about classification tasks, one major type of supervised task is simply classification. Output is a discrete category. Think about that email example. Categories might be spam or not spam. That's classification. In malware detection, might be malware or not malware. Maybe intrusion detection, attack traffic versus normal traffic. But we've labeled that data in one way or another. We've classified that data. Classification, of course, can also involve more than two categories. For instance, maybe there's a malware classifier. It might distinguish the subtype of malware. So it might be ransomware, a Trojan, a worm, or an adware, or something like that. Traffic classifier might separate traffic for network purposes into web browsing, video streaming, file transfer, or suspicious activity. Key point is that classification assigns inputs into one of several buckets, classifies those inputs into one of several classes. Second major type of supervised task is regression. Instead of categories, the output is a continuous numerical value. Imagine that you're trying to predict the CPU load of a server in the next minute or so. Well, that's a regression problem. Maybe you want to estimate how many packets per second a connection will generate. Again, regression. Another example is forecasting the time until a component fails, maybe based on sensor readings. Those are all examples of regression type tasks. Regression problems are less common in cybersecurity than a classification problem, but they're still important. For example, predicting that system load can help anticipate a DOS attack, a denial of service attack, or it can help us prevent resource exhaustion. And thinking back to one of the cybersecurity principles around availability, well, resource exhaustion, having no memory left or no CPU left or no disk left or something like that, would affect availability in that CIA triad that we talk about for cybersecurity. Let's look at the workflow then for supervised learning. First, you need a labeled data set. You need something that the data set has both features and a correct label. So it has some types of inputs and then a label that is appropriate for whatever classification is being used for that. So a data set of network flows would be an example, and it might be labeled attack or normal. And we might have things like source IP, destination IP, the ports involved, and so on. Those are all part of that data set. Those are all features of that data set. And then we have a label within that. Each row would have a label associated with it within that data set. So you split the data into two different parts. You split it into a training set and a testing set. And the next thing you do then is train the model. That means you run an algorithm like a decision tree, logistic regression, support vector machine, things like that. And those look for patterns to try to connect the inputs to the outputs. And then you take that test set, meaning that the algorithm hasn't seen this set of data yet, but it's pre-labeled. You know behind the scenes what it's supposed to be, and you run your algorithm on that test set. So that'll give you the classic statistic type stats on it, classic statistical outcome, if you will, like accuracy, precision, maybe an F1 score, those types of things. All the statistical means that we would have to measure whether something is successful, whether there's been a correlation there, and so on. And once you're satisfied with how that model is performing, you deploy it to the real world, maybe part of an intrusion detection system, maybe a malware scanner, and so on. That's the basic workflow for supervised learning, those 5 steps. Of course, there's significant work involved in all of the steps, but definitely in steps 1 and, 1 is where you might spend the most amount of time. Simply collecting labeled data, making sure that it's labeled correctly, splitting things as we can do programmatically, and then training the model and finding that is another area where you'll spend some time. Let's look at an example then. We've been talking about spam. Let's look at malware instead. So we have some inputs. We have the file size, the opcode frequencies, the entropy with the file itself. We might be looking at entropy on that file's contents, maybe the number of imported libraries, and so on. All of those things can be inputs to our malware classifier. And each file in that data set we've already pre-labeled. We labeled it ransomware, Trojan, worm, and so on. And now we split that. So we split that data set that we have of pre-classified data, and we train. The next thing we do is train to map on the test data. So once it's trained, we can take a brand new file, look at its features, and predict the most likely malware family, what type of malware it is. So this is enormously powerful in practice because new malware appears every day. And again, if the attacker just simply changes one thing, we don't want our algorithm to miss it. We would like our algorithm to say, hey, this might be malware. We might want to stop for a moment or quarantine this bit of this program that came in and put it off to the side so you can take a look at it and make sure that it's not malware or that it is truly malware. Evaluating supervised models requires much more nuance than just asking how often is it right, though. Accuracy is the simplest metric that we have. What percentage of predictions were correct? The problem in cybersecurity, though, is that accuracy can be misleading. So imagine a data set where 99% of the traffic is normal and only 1% of the traffic is representative of an attack. A model that always predicts normal will be 99% accurate. So think about that. If most of our traffic is normal, which it usually is, then if we just simply deploy a model that says if true, then assume that this traffic is normal, or while true, assume the traffic is normal and loop on that, well, 99% of the time, we've had an accurate model. So accuracy doesn't tell the whole story. That's why we use precision and recall. Precision tells us of the times that we predicted attack, how many were actually attacks. And recall tells us of all the attacks that actually occurred, how many did we catch? The F1 score is important here. It combines precision and recall into a single measure using their harmonic mean. It balances the trade-off between catching attacks and avoiding false alarms. We'll talk about these metrics as we continue to move forward, just introducing them now, introducing that so you have something to refer back to. Those metrics are critical for cybersecurity. False negatives, things that are missed if we miss an attack, or a false positive, so think of that as a false alarm, both have serious consequences when we're working with cybersecurity. Supervised learning has a wide range of applications in cybersecurity. Intrusion detection systems often rely on supervised models that are trained on labeled traffic. Malware classifiers, just as we just saw, also do the same thing. Phishing detection is also heavily supervised. Data sets of labeled phishing versus legitimate emails are used to train models that can spot suspicious links, odd wording, or unusual sender addresses. You don't normally get email from this person. That might be something that we watch with a supervised model. In financial systems, supervised learning is used for fraud detection. Credit card companies train models on millions of transactions labeled as fraudulent or legitimate so they can flag suspicious purchases in real time. Key is that each of these cases we have labeled data. We know which examples are good, which are bad, and we use that knowledge to train the models that can then generalize. Supervised learning, of course, is not without limitations. The biggest is that supervised learning requires labeled data. Labeling data is expensive. It's time-consuming. For intrusion detection, you might need experts to review the logs and decide which entries are attacks. That is highly labor-intensive, given the amount of traffic that we would normally have on a reasonably sized network. Labels can be noisy. They can be incorrect. Human analysts can make mistakes. Different analysts may disagree on whether something is representative of an attack or whether it's normal traffic. What's your definition of normal? Would be a classic discussion that would go on between security analysts. Another limitation is vulnerability to concept drift. Attackers don't stand still. They constantly change their tactics. A model trained on last year's attacks may not perform well on today's. That's a classic scenario as well, where we are working with some data and we are now very well defended against port scans. Well, the next attack doesn't occur. The precursor to the next attack is not a port scan. That's how they did it last time. They found an open port, and now we've deployed something that, based on if the traffic looks like a port scan, we block the IP temporarily. The next attack comes through a completely different way, and suddenly the defense that we had placed to prevent the attack didn't matter at all. So whatever we spent and whatever time we invested in that defense didn't help with the next attack that we have. Perhaps the most serious limitation is supervised learning often fails on never-seen-before attacks. So if it's a completely novel attack, a new kind of malware looks nothing like our training examples, the model's going to or may miss it entirely. That's where we talk about unsupervised learning and anomaly detection methods. And that's why those are important in cybersecurity. Some of the key takeaways then from this section of the lecture: supervised learning. When you think about supervised learning, think about data that's already been labeled. It's already been classified. And we have two types of classification. We have the bucket method, which would be traditional classification, spam versus not spam, versus something that's a continuous number where we would use regression. Our workflow in supervised learning is to collect and label the data, split that data into training and test sets, and then train on the training data, test on the test data set, and deploy our model. Supervised learning is widely used. It is limited, though, by the challenges that we discussed around labeling. That will wrap up this section of the lecture. Part 2 of the lecture will be available for you to watch, and we'll pick up from where we are now with Part 2. Thanks for watching.